This unknown tutorial is about the Usanovich acid-base definition and theory. Usanovich proposed this theory in 1939. Based on the Usanovich acid-base theory, acids react with bases and give up cations or accept anions or electrons, while on the other hand, bases react with acids and give up anions or electrons or accept cations. In simple words, a Usanovich acid is a cation donor or an anion or electron acceptor, and a Usanovich base is an anion or electron donor or a cation acceptor. So we have the Usanovich acid-base definition and theory. Based on which acids are capable of donating cations to bases or accepting anions or electrons from bases. On the other hand, bases are chemical species capable of donating anions or electrons to acids or accepting cations from acids. Let's consider some examples. As the first example, consider the reaction between ammonia and hydrogen chloride, either in the gas phase or a solvent in solutions. This reaction yields NH4Cl, ammonium chloride. In this reaction, we have transfer of H plus, a cation, from HCl to NH3. HCl, acting as a cation donor, can be considered as a Usanovich acid, while NH3, acting as a cation acceptor, can be considered as a Usanovich base in this reaction. As the second example, consider this reaction. Which can happen in molten or in molten inorganic mixtures. In this reaction, we have transfer of O2 minus, the oxide ion, from CaO to SiO2. CaO, acting as an anion donor, can be considered as a Usanovich base, and SiO2, acting as an anion acceptor, can be considered as a Usanovich acid. The third example is this reaction. In this reaction, the nitrogen atom of the ammonia shares its lone electron pair with the boron atom of the BF3. NH3, acting as an electron donor, can be considered as a Usanovich base, and BF3, acting as an electron acceptor, can be considered as a Usanovich acid. As another example, consider this reaction. In aqueous solutions, in this reaction, we have transfer of electrons from zinc atoms to copper to cations. In this reaction, zinc acting as an electron donor can be considered as a Usanovich base, and Cu2 plus acting as an electron acceptor can be considered as a Usanovich acid. As another example, consider this reaction. Mg2 plus SO4 2 minus yields MgSO4. The magnesium cation and sulfate anion combine each other to produce this ion pair in aqueous solution. In this reaction, magnesium accepts an anion, so it can be considered as a Usanovich acid. On the other hand, the sulfide anion accepts an cation, so this can be considered as a Usanovich base. We can consider many examples like these chemical reactions. And we see that Usanovich acid-base theory includes many different types of chemical reactions. For example, this reaction is also a Bronsted-Lowry acid-base reaction. This reaction is a Lux-Flood acid-base reaction. This reaction can be considered as an example of Lewis acid-base reaction. This is an example of oxidation-reduction or redox reactions. This is an ion association reaction. We see that Usanovich acid-base theory is very broad and it includes very different types of chemical reactions. In fact, it is the broadest acid-base theory and includes all other acid-base theories. Besides, it includes the oxidation-reduction reactions. Oxidizing agents or oxidants like Cu2 plus accepting electrons are Usanovich acids, while reducing agents or reducers acting as electron donors are Usanovich bases. While Usanovich acid-base theory includes many reactions, there are also reactions which don't fit into this theory. For example, let's consider dimerization of nitrogen dioxide, which is dinitrogen tetroxide. Lewis structures are as follows. In this reaction, every nitrogen atom shares its only lone electron with a second nitrogen atom. which one is the Usanovich acid here? Which one is the Usanovich base? So we see that this reaction doesn't fit into the Usanovich acid-base theory. On the other hand, let's consider the dimerization of Al3, which yields Al2Cl6. Lewis structures are as follows. We see that in this reaction, these two chlorine atoms share their lone electron pairs with aluminum atoms. These chlorine atoms, as electron donors, can be considered as Usanovich bases, while aluminum atoms, acting as electron acceptors, can be considered as Usanovich acids. So, Usanovich acid-base theory doesn't include this dimerization, but it includes this dimerization. Anyway, while there are many chemical reactions which fit into Usanovich acid-base theory, there are chemical reactions which don't fit so. Usanovich acid-base theory is very broad. It includes many chemical reactions. It is common in literature to state that Usanovich acid-base theory includes not only all other acid-base reactions, but all other acid-base theory, but also it includes oxidation-reduction or redox reactions as a special case of Usanovich acid-base reactions. This is important to discuss as redox reactions are important in chemistry. However, I think there is a problem with consideration of all redox reactions as Usanovich acid-base reactions. Let's discuss this by examples. Let's consider two redox reactions as follows. 2Ag plus and zinc yields 2Ag plus Zn2 plus, zinc cation. And the second redox reaction, 2H2 plus O2 yields 2H2O. In the first redox reaction, the oxidation state of zinc increases from 0 to 2, while the oxidation state of silver reduces from 1 to 0. In this reaction, electric charge and associated electron transfer are real. On the other hand, the situation is somehow different in the second reaction. For this reaction, Lewis structures of reactants and products are as follows. the oxidation states are like this. In this redox reaction, the oxidation state of hydrogen atoms increases from 0 to 1, while oxidation state of oxygen atoms reduces from 0 to -2. But these charges, these oxidation states, and their associated electron transfer are not real. They are formal. We really don't have any H plus cation in H2O water molecules. Each hydrogen atom in this side of reaction has 2 electrons in its valence shell. Again, each hydrogen atom has 2 electrons in its valence shell in the other side of the reaction. There is no formation of H plus cations here. These oxidation states, these numbers, these electric charges are not real, they are formal. Indeed, in water molecules, oxygens are negative and hydrogens are positive, but their charges are partial, not complete. We only have partial transfer of electrons from hydrogen atoms to more electronegative oxygen atoms. For example, the electric charge of hydrogen atoms in water molecules is plus delta, while that of oxygen is -2 delta, where delta is smaller than elementary charge, E. So these oxidation states, these charges and associated electron transfer are not real. They are formal. Or from another point of view, here we only have partial transfer of electrons, not complete transfer of electrons. So we see we can consider 2 different types of redox reactions. Redox reactions in which transfer of electrons is real, redox reactions in which transfer of electrons is formal, or from other point of view, it is partial. Based on the Usanovich acid-base theory, definitely Usanovich acid-base theory includes this type of redox reactions. Here, oxidizing agents are Usanovich acids and reducing agents are Usanovich bases. So Usanovich acid-base theory definitely includes this type of redox reactions, the redox reaction in a narrow sense, as Usanovich acid-base reactions. On the other hand, if we want to assume that Usanovich acid-base theory also includes this type of redox reaction, or in fact all redox reactions in a broad sense, then we should also assume that in addition to complete transfer of electrons, in Usanovich acid-base reactions, we can have partial or formal transfer of electrons. Or acids, Usanovich acids, may also accept electrons partially or formally. Or Usanovich bases may donate electrons also partially or formally. Anyway, it is common in literature to state that Usanovich acid-base theory also includes redox reactions. But it is good to pay attention to such narrow points. We see that Usanovich acid-base theory is very broad, and it includes many chemical reactions as acid-base reactions. Some criticize Usanovich acid-base theory because of this. They state that Usanovich acid-base theory is so broad that it almost includes all acid-base, all chemical reactions. And because of this, we don't need to talk about acid-base reactions. We can simply talk about chemical reactions. Besides this, when the range of a theory gets bigger, it usually also becomes harder to use. On the other hand, some others believe that we can criticize Usanovich theory in this way. They believe that the border between acid-base reactions and other chemical reactions, non-acid-base reaction, is not well defined. For example, consider this reaction. The reaction between pyridine and an oxygen atom, in which the nitrogen atom of the pyridine shares its lone electron pair with the oxygen atom. Here, pyridine acts as an electron pair donor, so as a Lewis base, and the oxygen atom acts as an electron pair acceptor, so as acts as a Lewis acid. So this is a Lewis acid-base reaction, where Lewis acid-base, the usage of Lewis acid-base theory is very common in chemistry. So we can consider this as a common acid-base reaction in chemistry. On the other hand, this reaction is also an oxidation-reduction reaction, a redox reaction. So the borderline between acid-base reactions and redox reaction is not clear or well defined. And because of this, scientists believe that the aim of acid-base theories is not to separate some reactions as acid-base reactions. They think that any acid-base theory can be useful in its own for some specific purposes. They think that each acid-base theories may have its systematizing power, which could be useful in some area. So they think we shouldn't judge acid-base theory by how broad they are, or by the fact that how many different types of chemical reactions they include. Anyway, we see that Usanovich acid-base theory is very broad, and this is both an advantage and also a disadvantage for this theory. Here it is also good to consider all discussed acid-base theories together. We already have discussed Arrhenius acid-base theory, Bronsted-Lowry acid-base theory, Lewis acid-base theory, solvent system definition or acid-base theory, Lux-Flood acid-base theory, and finally Usanovich acid-base theory. Based on Arrhenius acid-base theory, acids are H plus producers in volume, and bases are OH minus producers in volume. On the other hand, based on the Bronsted-Lowry acid-base theory, acids are H plus donors in any given situation, and bases are H plus acceptors. Based on the Lewis acid-base theory, acids are electron pair acceptors, and bases are electron pair donors. Based on the solvent system definition, acids are Solvonium producers in a solvent, Solvonium, or the characteristic cation of the solvent, or the cation produced by self-ionization of the solvent. And bases are solvate producers. Or the characteristic anion of the solvent, the anion produced in self-ionization reaction of the solvent. Based on Lux-Flood acid-base theory, acids are oxide acceptors, and bases are oxide donors. Finally, we have the Usanovich acid-base theory, based on which acids are, in simple words, cation donors or anion or electron acceptors. On the other hand, bases are anion or electron donors or cation acceptors. These are different acid-base theories whose discussion is common in chemistry textbooks. When we consider all these acid-base theories together, we can easily find a fundamental similarity between these acid-base theories. In all of these acid-base theories, acids are chemical species donating cations or accepting anions or electrons, and bases are chemical species donating anion or electrons or accepting cations. Acids, in all of these theories, acids donate positive species. H plus in water in Arrhenius acid-base theory, H plus in Bronsted-Lowry acid-base theory, Solvonium in solvent system acid-base theory. Or acids accept negative species. Electron pair in Lewis acid-base theory, O2 minus in Lux-Flood acid-base theory. On the other hand, in all of these acid-base theories, bases donate anions or electrons. OH- in water in Arrhenius acid-base theory. Electron pair in Lewis acid-base theory. Solvent in solvent system acid-base theory. O2- in Lux-Flood acid-base theory. Or bases accept cation or positive species. H+ in Bronsted-Lowry acid-base theory. Also, we see that Usanovich acid-base theory highlights this fundamental similarity and includes all other acid-base theories. So we see here that acids are chemical species donating positive species or accepting negative species, and for the bases this is the reverse. From electric interactions, we know that opposite charges repel each other, interact each other, while like charges, for example, two positive charges, two negative charges, repel each other. If we assume that donating is like repelling and accepting is like attracting, we can consider an analogy between acids and bases on one hand and positive and negative charges on the other hand. In this analogy, acids are like positive electric charges and bases are like negative electric charges. Acids as positive electric charges donate or repel positive species, while bases as negative electric charges accept or attract positive species, and vice versa. So here we see that acids are associated with positivity or positiveness, and bases are associated with negativity and negativeness. We can see many examples in context of acids and bases that chemical species with a high positive charge on one of atoms or on the whole species usually behave well as acids, while on the other hand, chemical species with a high negative charge on one atom or on the whole species usually behave well as bases in all of these acid-base theories. This generalization here looks very simple, so simple that it might look incorrect for us. We expect that acid-base behavior to be much more complicated than this. Of course, there are many contributing factors to the acid-base behavior of a chemical species, but this generalization in many cases can be useful, and in fact it is more fundamental than it may look than an apparent analogy. Whether a chemical species will behave as an acid or as a base in any of these acid-base theory depends on its structural properties, and among those structural properties, value and sign of electric charge on atoms are very important and play an important role in determining the acidic or basic behavior of substances. So it is good to remember this generalization, of course with its limitations. with consideration that it also has some limitations. So after all, we see that there exists a fundamental similarity between all these acid-base theories, and they are somehow connected to each other. As this fact is highlighted by the Usanovich acid-base theory. We see that there are different acid-base theories. After all, which one of them is true? In the context of acids and bases, we can discuss that an acid-base theory is true or false. Acid-base theories are different from other theories in other fields of science in the way that there are just definitions. One acid-base theory assumes that acids are chemical species with a specific property, while another acid-base theory assumes that acids are chemical species with another specific property. There are just definitions. We can we can prove that they are true or false. Here we should discuss about the fact that whether one acid-base theory is useful for a specific purpose or not. Acid-base theories have different scopes. The usage of one acid-base theory may be preferred over others in a specific area of science. For example, for elementary discussions of acid-base behavior in aqueous solutions, we may prefer Arrhenius acid-base theory. For calculation of H+ concentration in amphiperiodic solvents, we may prefer Bronsted-Lowry acid-base theory. For electrophilic or nucleophilic reactions in organic chemistry, we may prefer Lewis acid-base theory, and so on. So, the range of these theories, the applications are different. And in a given situation, one acid-base theory might be preferred to others. One might look more right than others. But after all, they have a fundamental similarity, and it is good to be familiar with all these theories and consider the fact that each of these theories may be useful in a specific area. This is the end of this online tutorial. I hope you find it useful.